So thank you everyone so much for coming. Um, really excited to be here. I'm Jay. I love math. Um, I'm a little bit strange in that way. I always felt like I was a little bit different than the heliophysics community because I seem to I always see connections that others can't see, and I really the reason why I love this drive center is because it might maybe maybe possible for me to finally help out in ways that I've always wanted to. And so with that, heliophysics is currently multidisciplinary. If you think about what it means to be, if you think about this as like, you know, a disciplinary would be just silos as like a plate of fruit. You just got a random orange with an apple, and the multidisciplinary is when you have like a fruit platter. Maybe the kiwis want to mingle with the apples, and it's organized in some way. Um, the interdisciplinary approach is like the fruit salad. And that's sort of what I think this drive center is aiming at. And so you're fundamentally creating something different with a fruit salad. It's a new dish, but then I think the goal would be a higher level synthesis of that was to make a smoothie. Then you're fundamentally creating something different. That's transdisciplinary, and so in a smoothie, there's no discontinuity between a grape and a banana. It's just there. There's no limit. And so with that, I'm just going to start talking about what I thought about last Sunday. I drew this picture. I was laying on the couch and I drew this picture of the sun, of the heliosphere. So here's the sun. Very happy. Lots of seeing me at the Earth, but the Earth is fine. Very happy because it's got a nice shield. We got the planets over here. We got the G cloud. I just recently learned about the G cloud. Apparently, we're gonna run into it soon. Maybe scary. Okay, so here are the different regions of the heliosphere. As you know, there's the solar, and those are explosive energetic events. And then we have people who study inner heliospheric stuff, so solar wind physics and turbulence, and with particle interactions. Although they exist everywhere, most people study it in the terms of the solar wind, but these are sort of energy transport pathways. We have the planetary folks, and they deal with energy coupling within the heliosphere. And then we have the outer helio folks, say stuff like galactic cosmic rays and ENAs. What's the shape of the heliosphere? And the interaction with the local interstellar medium and the LISM and the ISM. And so these folks study the energy coupling between the heliosphere and the interstellar medium. And so I like to think about the heliosphere in more general context in terms of just energy flow and energy coupling. Okay, I want to talk about Leonardo da Vinci. Leonardo da Vinci was an incredible human being because, not only did they create magnificent art such as the Mona Lisa, they created this amazing book, the Poetis Atlantico, in the year 1500, and in that book, they drew inventions that were never thought of. They drew a bicycle. They drew the first images of flight and archery. Musical instruments. The concept of pulling a lever was drawn in that book, and it's just incredible. Back then, the artists were the ones that were the scientists. And Leonardo da Vinci was actually the first one to draw turbulence in water, and they were the ones to coin the term La Turbulenza. And without this drawing, people wouldn't be able to conceptualize what turbulence is. And so what's interesting about this is that, if you read, try to decipher this Da Vinci Code, um, they ask three really important questions that are still relevant today. Where is turbulence in water generated? Where is turbulence in water persist for long times? And where does turbulence in water come to rest? So just to give a really brief historical context, Da Vinci did their drawings in 1500, and that was 137 years before Rene Descartes said, "I think, therefore I have a coordinate system." Just appreciate that for a second. 137 years before we could even have the concept of a function, a map, a domain and range. All we had were drawings. And so thank you, Rene Descartes, because then that allowed for the invention of calculus by Leibniz Newton, in the mid 17th century. And then, once we had a nice, formulation of calculus, Navier-Stokes came around in 1822, and they had their famous equations for describing motion of a viscous fluid. And then we had Reynolds came along to classify the condition for which we had a turbulent flow. And so, just for those who may not be familiar, we have in a flow, we have the smooth part, which is a laminar part, and then it transitions to more just expansion, dissipative, into turbulence. Okay, so a little bit about the Navier-Stokes equations. Every physics problem starts with F equals ma. So let's say we have an incompressible viscous fluid with some flow velocity u. In mathematical terms, that just means this, that divergence to zero. And so F equals ma. So we have our force terms over here. We have pressure, and then we have a viscous linear term. And then we have our mass. Our mass is kind of like the density, linear mass density. And then we have our acceleration. And so that is the sum of the instantaneous time evolution of fluid plus a nonlinear term. So Reynolds was like, hey, what if we just took the ratio of the nonlinear term to the linear term? And so this is proportional to some length scale L. And what they said was, okay, well, if this fraction is greater than 100, then that means that the nonlinear term dominates. And that means that turbulence ensues. What I will say is the reason why the Navier-Stokes problem is so interesting is still today mathematicians are trying to prove whether or not the Navier-Stokes equations, that existence and smoothness, it doesn't exist in three dimensions. And so what does that mean? It means that a lot of people try to model turbulence in 2D, but you don't get all the physics, because in 3D the mathematics is fundamentally different, and not only is it different, it's fundamentally unsolvable in 3 dimensions. And so I just wanted to point that out. Okay, so what I wanted to say really quickly is that the form of this equation is exactly analogous in the magnetohydrodynamic case, really quickly, in terms of the L-cells or variables. We just take this, so, we had the linear term of and a nonlinear term of propagation of alphane waves. And so when the nonlinear term dominates, it leads to transfer of energy to higher wave number. And so this is kind of like the connection between the hydrodynamic case and the MHT case. And so just really quickly, I made this visualization of alpha and waves colliding, and I have some papers if anyone wants to read them. Shameless plug about how to visualize um, alpha and wave collisions, and how and that you can see at every collision more and more uh, current sheets are forming, and more dynamics, and so just interesting. You can actually, there's a PDF embedded in this paper, which is really interesting. But anyway, um, moving on. So um, I don't know if anyone drinks coffee. Hopefully, I mean, we're talking to a bunch of scientists, so uh, if you mix cream into coffee, I don't know if anyone noticed that it just takes one or two stirs for the cream to evenly mix. Why is that? If you try to do that with paint, if you try to mix two different colors of paint together, it's not really going to mix. Well, that's because paint is very viscous. And so it's hard for that nonlinear term to dominate over that viscosity of the linear term. But in water and coffee, uh, it's not very viscous. And so it's a turbulent medium. So we have Richardson comes along, a weatherman, in 1920, and they said big worlds have little worlds that feed on their velocity, and little worlds have lesser worlds, and so on to viscosity. And so taking that concept again of just stirring that cream into coffee, we have one, large scale injection of that stir at some length. And then that large stir turns into two smaller stirs at some constant frequency rate. So, this large stir turns into two small stirs. It doesn't turn into 30 small stirs. And then those two small stirs turn into four, nonlinear, and so on to heat. And at some small scale, it's eventually just dissipates. So then we had Kolmogorov came along in 1941. He was a Russian mathematician. He was a category theorist, had nothing to do with fluid dynamics. If you read his original paper, it has nothing to do with turbulence at all, which is funny. But anyway, so he came along and he had this idea where we have this famous spectrum of the log of the kinetic energy of the system versus the wave number. So it's just the inverse of the length scale. So we have the energy injected at some driving scale. So that's when we're mixing that cream, and then that cream, the eddies, the swirls, they cascade to smaller scales at a constant rate, some constant rate in p. A lot of people argue about what this number is. That's where the 5/3 come in. And then at some viscous scale, the energy gets dissipated and it falls off. So, and the same is true in the hydrodynamic case and the magnetohydrodynamic case in the solar wind. So we have some energy containing range. So let's say we have a CME comes by or something, and there's some large scale energy, and then there's the inertial range. So that constant number is 5/3, and then the dissipation range. And a lot of people argue about what this number is, but it's a constant, and that's what's important. So the ultimate goal in turbulence is to understand the dynamics of this entire cascade of energy to plasma heat. This transition region from the inertial range to the dissipation range occurs at the scale of the ions, and that is usually the missing puzzle piece. Okay, so now everyone probably knows this picture. Um, we have the coronal heating problem, uh, and Parker Solar Probe is hopefully gonna figure some stuff out about it. Um, that same picture I just showed is true observationally. So this transition region is the main puzzle piece, and how, you know, a lot of people try to think about, okay, how does the turbulence dissipate? So what are the different mechanisms for turbulent dissipation? Um, it could be stochastic heating, magnetic reconnection, uh, dissipation of energy into coherent structures such as current sheets, and wave particle interactions. So that's what I like to study, and specifically, I like to study resonant wave particle interactions that occur at the length scale of an ion. So Parker Solar Probe has now completed its first, let's type out 8 orbits around the sun. But what do we learn so far about the energy transfer leading to solar wind thermalization? Okay, so now I'm going to be moving on to some work we're doing with Parker Solar Probe. So I love to study distribution functions because they are incredibly interesting. When energy transfer only occurs when a distribution is out of equilibrium. And so equilibrium means, just a Maxwellian, but it's really interesting when the distribution function deviates from a Maxwellian. So a Maxwellian is extremely symmetric. And so you can think of it as studying asymmetric components of the distribution is actually studying the non-Maxwellian features. And so one way that particle velocity distribution functions, I will now say VDF for that term, so they can lead to wave growth. For example, here's a bump on tail instability, where particles moving slightly slower or faster than the wave phase velocity can participate in a resonant interaction, and that can lead to energy transfer from particles to waves. And so what I like to do is I look at these things called beams observed by spin ion, which is a subset of the particle instrument on the Parker Solar Probe sweep. And then I look at the electromagnetic field data from fields to try to see if we can find energy transfer in wave particle interactions. A little bit more about spin ion. It's right here on Parker Solar Probe, and it's an electrostatic analyzer. And it measures 3D ion distributions. It also has a time of flight feature, so it can separate protons from alphas and other heavy ions. The caveat is that it's partially obstructed by the heat shield, so we can only measure partial moments of the distribution. But luckily, eventually we're going to be creating a merged data set with SPC, which is a Faraday cup looking directly at the sun for a more complete moment. But the benefit of using spin ion data is that the flanks of the distribution are the most useful for detection of beams or other asymmetric components of the velocity distribution function that could be leading to energy transfer. Okay, so one of the first observations of proton beams or asymmetries in the VDFs was observed by Helios. Here's the famous Marsh paper in 1982. Here's an example of a symmetric Maxwellian distribution, just a circle in velocity space Vx Vy. But then you can see how asymmetric these VDFs can be just by these drawings here. Here is one example of a 1D case of the of a double bi-Maxwellian observed in encounter 2, Parker Solar Probe, where typically we model distributions as as a sum of 2 bi-Maxwellians. So one is the core of the distribution, which is kind of like the average, the bulk flow, and then there's the beam. So here is a shameless plug again. First results from Parker Solar Probe included this really, really cool event about 2 years ago, I guess, about a really incredible simultaneous wave particle energy event. And so I'm just going to go over what these panels are really quickly before I play the animation. So we have, here is a 3D representation of the VDF. Here are some 2D representation, or 3D, or I guess these are also 3D. These are just contours. So this is VZ, VR. This is in the SpanEye instrument frame. And in here, this panel, the reason why this is cut off is because of the heat shield. So I like to plot this panel as well, just to see how much of the VDF is cut off by the heat shield, and can we trust the measurement. These arrows here represent the direction of the magnetic field, and the length of the arrow is the Alfvén speed. These panels here are just, so the first panel is a wavelet transform of the fields data. So you can see that there was power at many scales, and then all of a sudden there was a narrow band coherent wave storm at the ion gyro frequency, which is this dashed line. And then that gave a polarization signature that was left-hand polarized in the spacecraft frame. And at the same time, there's this great outburst of differential energy flux measured by span ion. So we're just going to let this movie play really fast so we can see the time bar here. And as you can see what happens as we go through the wave storm and what the evolution of these VDFs look like. So you can see that once we enter the wave storm, the beam just becomes ginormous and is out of control. And so this is sort of the event that captured my interest, that I got to keep an eye on these VDFs, because they're acting pretty wild. And it's written on the stalls of the cosmic bathrooms that the information carried by these VDFs is going to tell you about the direction of the energy flow. So I'm going to let this movie play a little bit more, and for the sake of time, I will move on. Does anyone have any questions so far? I'm going a little bit fast. Silence.
Do you prefer to get questions during the talk, or do you?
We can talk whenever.
Okay, so if there's anyone who has any questions, go ahead and ask, please. If not, we'll have some at the end. Don't worry, Jay.
It's okay. All right, I'm going to move on. But in closing, one of the clues from this first paper was that we did instability calculations with something called plumage, and we found that the proton beam was mostly responsible for the instabilities that occurred. Okay, so that was from encounter 2, orbit 2. Encounters 4 and 5 and 6 and 7 and 8 all have this really interesting dynamic to it, where the inbound orbit was completely different than the outbound. I want to know why. And that's sort of what my quest, one of my quests is right now. So here's one example. So here's encounter 4. The first panel here is position from the sun. So you can see that we got down to less than 30 solar radii on this encounter. Here's the density, velocity, and temperature. So on the inbound, so as we're approaching the sun, it's all 3 of these parameters are fundamentally different as we go in out. The wind got so slow, the temperature got very cold, and this is a pattern that's been happening with every encounter, and it's very, very interesting. Here are some other just same parameters as I showed previously. This is magnetic field, wavelet transform of magnetic field. This is the polarization signature, where right-handed is, or sorry, what red means right-handed in the spacecraft frame, and blue means left-handed. And this is the energy flux. So what was really interesting about this encounter, as opposed to the other ones, is that there were these really interesting patches where there was just hours and hours and hours, even days, of right hand right hand, possibly magnetosonic waves. I've never seen that before. And so during one of these storms, this is an 8-hour period where there's these right hand polarized waves. We see these really interesting structures in the VDFs, the proton VDFs. Just to explain these panels, this panel here is the radial magnetic field, so BR over B. I don't know if a lot of people talk about switchbacks, and so this is my little switchback parameter. Okay, how much is the radial magnetic field changing, which is a good quantity to plot. And then we have magnetic field, and I already explained what these were. And then we have the velocity. So we can see that the velocity is the solar wind velocity is only 200. It's only 200 kilometers per second. And the length of this arrow is the Alfvén speed. The Alfvén speed was about 80. So the solar wind Mach number here was about 2, which means that we really can't use the Taylor hypothesis is starting to break down, and we can't use some simple approximations to calculate the Doppler shift to try to figure out, okay, what's the frequency in the plasma frame. Things are becoming very difficult. But I think that it's really interesting. So that the axes here are actually normalized by, this is actually in the plasma frame, it's normalized by the Alfvén speed. So you can see, at 4 all the way up to 4 Alfvén speeds, we get this very large beam that looks like a hammerhead shark, and that term stuck, and so I'm gonna keep using it. And it follows, and the trajectory of these particles follow these contours, and I'm going to briefly explain what those contours could mean. Just to give some more context, since we were talking about turbulence, if you take the average power spectrum over the 8-hour period and plot against frequency, the location, we get the injection of energy, and then we get this nice inertial range, the constant slope, and then all of a sudden we have this extra, the knee, that's what people call this, a knee, this extra power bump, and that is exactly the location of these waves as predicted. Moving on to what those contours could mean. If you take the plasma, the cold plasma dispersion relation for a magnetosonic wave, this is that equation, and then we have some of the variables are. And then we have this resonance condition for producing the magnetosonic wave would be the n=1 condition. And so then if you plot both of these curves, you can see, okay, where do these curves intersect? And that would give you the minimum velocity such that these beams, the particles would have to be at to participate in this resonance interaction. And it happens, we got this number at 2.6 times the Alfvén velocity. And so we'll be talking about, so there's this low K resonance. So it actually intersects at 2 points, at a low K and a high K. I'll be talking about the low K. So at the low K, particles lose energy by diffusing along these solid lines. And so these fast magnetosonic waves are unstable and grow, and the protons theoretically diffuse rapidly along the solid line contours. That's what, you would get this by just mapping this to this. And then the same is true for alphas. You can do the same calculation. And indeed, we define this feature in the alpha particle velocity distribution functions. Here's one example from encounter 4 again. But it's kind of interesting every time I see these features in the alpha velocity VDFs. It's when there is concurrent polarization signatures. There's both right-handed and left-handed polarizations in the spacecraft frame, which could mean a lot of different things, but I just think it's interesting. So going back to the protons, so we have this interesting shape, and I've been trying to figure out how to decompose it to try to understand it. So we have this would be the core. So this is of the distribution, the population 1. And then we have this narrow part, and we're going to call that the beam for now. That's population 2. And then we have this other part, this population 3, the tertiary population, the hammerhead, which is extremely anisotropic, meaning T over T parallel is definitely a lot greater than 1 for this population. So because it seems like the protons are diffusing perpendicularly, maybe. And doing this work, we've kind of thought, these proton beams are really behaving like electron straws. And so what if we could unite the electron and proton community by just calling the beam a straw, because that's what it is, in the sense that it follows the magnetic field lines and everything like that. And so the straw, I think we should be thinking about maybe renaming terms even within our community, so that we can understand each other better. So because of this extra asymmetry, I felt the need to model the distribution instead by 3 triple bar Maxwellians. So here is just a close-up of just some of the, so this is actually the same time slice as this of the instrument, where we have all of these different panels right here represent, so this is the, we have 8 by 8 energies, 8 by 8 angles. So this is a close-up of just 3 by 3 of the phi and theta angles of the instrument. And so really what we're doing I'm hinting at is that, the more max lines that you put, we're really what we're doing is creating a basis. Um, well, that's a future project. I'm just going to show you a little bit about these fits. This is how, so we have our switchback parameter magnetic field. This is so by doing that, we got to do fits of the density and the temperature and all that stuff of the three different populations. Um, and we found some interesting stuff. And then we made some histograms. So I wanted to plot, the uh, the temperature anisotropy of that tertiary population versus some dimensionless quantities of the solar wind. Try to understand. I just thought that the temperature anisotropy of that population would give you an understanding of where of how to classify these asymmetries. And so one of the projects I'm working on right now is to try to understand, you know, why do these features arise, when, under what solar wind conditions, and stuff like that. So in this future project, I'm going to characterize some more kinetic instabilities, extend the analysis to the alphas, and try to do some modeling, work with some people doing modeling, and then I'll get to the wave particle correlator next. So really what I'm after is what is the origin of the VDF asymmetries, and how do those asymmetries contribute to energy transfer and plasma heating? But this question, what is the origin? The chicken or the egg problem? Is it locally generated by kinetic instabilities or something like that, or does it have solar origin? That chicken and egg problem seems to be common throughout multiple fields within heliophysics. And what if it's both? What if it's a combination? I've been seeing some interesting correlations with, for example, the more how asymmetric the distributions get as you approach the heliospheric current sheet, stuff like that. That's really interesting. Anyway, I can go on and on. I want to talk about the wave particle correlator. But first, I do want to talk a little bit about this idea of generalizing language, because these VDFs that break symmetry are carrying information about where the energy is going. And so, where does turbulence come to rest is really saying, where does the energy go? And that is really saying, where does the symmetry break? So using this universal language, we can talk to more people, and that would be really great. Cool. So I guess I already said this, but I'm really interested in how the asymmetries are connected with all of this other stuff with Parker Solar Probe and other spacecrafts. So I'll be focusing on the wave part of the interaction part at this moment. So there's this really interesting data set that I've been working with. It's called the wave particle correlator. And it's actually just this single cable that exists between the sweeping fields instrument on Parker Solar Probe. And it allows for the instruments to communicate with each other, and we can make synchronous measurements of particles coming in at the same time as fields, as waves. And but because it's only a single cable, It's difficult because it can only capture a very narrow energy range, maybe 3 energy bins. And so we're still trying to figure out the best way to do this. But this is a fun project that I've been working on for a little bit. Um, Before I get into that, I just wanted to go over a little bit of theoretical background. So I'm going to be talking about a technique that I use called the field particle correlation technique. And to explain what that is, I just wanted to briefly go over the Vlasov equation for kinetic theory and for as a refresher. So we have the Boltzmann equation, and the Lorentz term is the one responsible for the interaction between the fields and particles. And for the sake of argument, we're going to assume that there's no collisions. So the basic idea, I'm going to go through this a little bit quickly, so don't worry about it if you don't if you can't read the equations fast enough. But the idea is to measure the change in particle energy using measurements of the change of the distribution function. But this is integrated over velocity and space, and so it's not observationally accessible. And so instead, we want to focus on single point observations and time average. So then we can define a phase space energy density, W. But essentially, to isolate the physics responsible for the energy transfer, all we need to do is take a correlation of this term and the electric field. And we do that by doing this time average. And but after some integration by parts tricks, you can actually take the derivative part out of the equation and which is a lot easier to measure on board. And so then using this concept, I can explain a little bit more about the work I did a couple years ago that just got published in JGR last week. But first, I'm going to talk about Landau damping. I just want to hopefully everyone understands that Landau damping is an example of a resonant turbulent dissipation mechanism that comes about in wave-particle interactions. It's when the wave gives energy to the particles. And so if you think about surfing, the classic example is, if you're on your surfboard and a wave comes at you and you're not moving at all, it's not going to work out. But if you paddle at just slightly faster than the wave, then that wave can accelerate you. And that's sort of what happens in Landau damping. And if you think about, okay, what is the velocity space signature of Landau damping? It looks like this. And so if you plot it as, V parallel and V perp space, the correlation goes from negative to positive about some resonant velocity. And so this is the signature that we look for in velocity space if we want to look for Landau damping. Okay, so this is a lot of information, I realize. Basically, using the field particle technique, I wanted to see if Parker Solar Probe has sufficient phase space resolution to resolve Landau damping. And how I did this was I took a simulation that was in V parallel V perp space, and then I boosted it to the solar changed coordinates from V perp to energy in phi, and then I boosted to the solar wind velocity, and then I down sampled it to different spacecraft resolutions. In particular, I did Parker Solar Probe. Here's just a kind of like a map of how I did that. But basically, you can see that, here's the velocity space signature of Landau damping in really high resolution simulation. But then you can see where the grid space is. And then if you look at the sweep resolution, you can indeed resolve that same signature, even though it's not as fine. And so if you want to read about it, here it is. Then what I did was I discretized everything. And so, so here's for example, we have some fluctuation, some number density of particles, N of T. And then we have an electric field in red. If you think about, for example, so N of T would represent more. So N of T is a little bit higher right here. And so you can use Poisson statistics to try to say, okay, probability of counting a particle is more here. So there's more particles here, and there's less particles here, if that makes any sense at all. And so try to say, okay, like the particles come in as a sum of delta functions at some time. But I used the information from the simulation to calculate, okay, that probability. So it's kind of like a reverse situation I did. So then, so the wave particle correlator on probe can count particles with the high time resolution, synchronous with the magnetic field. So this algorithm called patch, particle arrival time correlations for heliophysics, is something that I really want to apply to the Parker Solar Probe data now that all the theory is worked out, because it gives a measure of the rate of change of phase space density due to the electric field as a proxy for J.E. And so basically, if you instead substitute the sum of delta functions, now sum of delta function is a distribution function itself, it's just not smooth. But if you substitute that in, you actually just get that, this correlation is just, it can be done by just summing the electric field at each particle arrival time, which is a very simple algorithm to implement on board a spacecraft. So why would you want to do this on board? It's kind of like another form of compression. There's so much bandwidth issues for getting all the data down. But what if you could do more averaging on board, such as this, and bring back those average quantities to try to save space. And so if you want, so I actually did a very careful derivation of reimagining kinetic theory instead of so I don't know if anyone knows about the Clermont-Dupré equation, but that is the equation that comes right before the Boltzmann equation. So the Clermont-Dupré equation actually keeps things in as a sum of delta functions, and and then the Boltzmann equation, that's done when you actually take an ensemble average of n of t, and an ensemble average may not be the best idea if we want to think about what are we trying to measure, because the ensemble average in a statistical sense is every the average of every, the every of the plasma that existed at all times everywhere, which is not observationally accessible. When we do the ensemble average, we're losing so much statistical information. And so what if you could reimagine all of this by not doing the ensemble average? Just something that haunts me in my sleep. But if you want to read about what I did, you can see the appendix of this paper. Here's a fun animation of starting with one particle and just seeing, okay, at what point does the velocity space signature resolve? It already did resolve, but as the number of particles increase, you can see that the velocity space signature is more and more resolved. That's interesting. Okay. So here's a very, very first attempt at what the actual data looks like from the wave particle correlator. It looks very similar to the cartoon I draw. So here is a wave packet. At the same time, we have counts. Each of these lines represents individual particle counts coming in. And so, and then you can see, try to figure out, from that single cable, okay, what energy bins are we in? And so each color here represents a different energy bin. So there's 4 colors, 4 energy bins. But the spacing in between each line is actually a different angle. So we're getting, angular coverage for sure, but not necessarily energy coverage. And so the idea here is to maybe, okay, well, what if we could figure out, what is the actual like resonant velocity bin, and what is, and could we just scan along, a narrow region where there's, we definitely see it. No, it could be resonant, and then definitely no, it's non-resonant. So there's just some things that I'm thinking about. And so then I tried to map it to a velocity space. This is energy theta, but you can see here that if you calculate the field particle correlation in the same manner that I just described, there is some sort of phase space bunching right here, and I don't know what that means, but this is just a fun project that I'm working on right now. That is definitely a rough draft. So I just wanted to close with some high-level math connection concepts. So I like to think about things generally. You can generalize magnetic connection and plasma instabilities. They're both mechanisms for sudden explosive energy release. The onset of sudden explosive energy release is analogous to a non-integrable solution of the dynamic system. The words integrable, solvable, invariant, and symmetric are all equivalent words. So my question is, can the study of energy storage and release in heliophysics be generalized to classifying the symmetries and asymmetries of the system? So where does the energy go? Where does the symmetry break? That's always my question. I'm gonna take a little pause. So when I was looking through my hard drive, and I randomly found this poem I wrote in 2016. I was very perplexed about my past self. I wrote this poem about entropy. No idea, but I'm going to read it to you. It says, love is chaos. Chaos is love. An irreversible process that is poorly understood. A mystery that humans have declared unsolvable. A system that is greater than ourselves. I am the coffee and you are the cream. we begin to mix, but as we mix, we do not know our fate. We couldn't possibly know that to be unmixed is that of a fallacy, a farce, an impossible task. For in love, to love and to be loved, the entanglement is too complex to be undone. I cannot unlove you. The coffee cannot unmix from the cream. So anyway, I love nonlinear dynamical systems theory. It's a class I took in grad school, and I've always been so fascinated by it. And I think that, in plasma physics, that set of particle orbits in 60 phase space forms a topological manifold. The word manifold might scare you, but that's okay. It just means that you can do calculus and everything's super awesome and great. But it's an incredible tool to predict sources and sinks within a system, identifying invariable and invariant and unstable configurations in phase space, characterizations of chaos, entropy, and ergodicity. If anybody wants to get it down into ergodic theory, which is the underpinnings of thermodynamics, please let me know. I love to think about it. And using dynamical systems could really explain these formations of coherent structures such as current sheets and how the energy may be trapped or dissipated within them. One more thing I want to mention that I is near and dear to my heart is studying magnetic topology through the braid group and topological non-invariance. And so this is just 2 examples of where reconnection can reduce topological complexity and liberate energy. That sounds familiar. And then here is something really, really cool. Don't worry about these numbers, but somebody calculated probabilities of how to untangle knots to get to a more stable state, which is really interesting. But anyway, I just wanted to close that, all of these things can be written in terms of, okay, where does the sun break symmetry? Where does energy transport break symmetry? Where does ITM boundaries break symmetry? And outer helio, where does this boundary break symmetry? And with that, I think the future of heliophysics is transdisciplinary. And I want to thank you.
Thanks, Jay, for a very comprehensive and fairly transdisciplinary talk, I would like to say. So let's open this up to questions. I have a few, but I'll let our audience ask questions first. I've seen 2 hands up. I'm seeing Bimson. If you would like to ask a question, go ahead now. I think you can unmute yourself, but I will unmute you. Bimson, can you hear me? Okay, well, that's interesting. And then I saw Carlos. Did you have a question?
Yeah, thanks. Thanks, Jay, for this awesome talk. So yeah, my question maybe is, do you have any clue about what is the mechanism responsible for the generation of the beam? There are different possible mechanisms that can lead to the formation of proton beams, mainly based on, I don't know, evidence from numerical simulations. It has been discussed many different possible mechanisms. So I'm just wondering about if you have any clue about what mechanisms can be producing these beams, and what is the relation with the waves that are typically observed in the measurements. So I'm just wondering about that.
Yeah, I think well, this is all guess, because it's an unsolved problem. I think it's it must be a combination of generated locally and solar origin, because they fundamentally behave different in different regions of plasma that are connected to, for example, when we go into the I'll go back to the event I was talking about. Thanks for humoring me with my poetry. Let's see. Sorry.
Enjoyed it.
Okay, so in this region is really crazy because it's only 200, which I think that we're going through a different a fundamentally different region of space that could have significance to maybe connected to some sort of I think the quiescent solar wind is what people are saying, is what it is. And it's interesting to think about, these features, these beams, the formation of the evolution of the beam. So I really think that this feature is a signature of how the beam is evolving at high energies, but it's just that the time scale, the time resolution of the instrument can't resolve it fast enough, and so that's why it looks like this, I think. But I think only time will tell what the answer is. Is really what I'll say.
Thanks, Jay. We have, I think we have Bimsen who wanted to have a question as well. We can come back to that after.
Can I ask a question?
Yes, please.
Okay, all right. I wanted to ask some clarification from Jay. When you say explosive energy release, are you talking about finite time singularity?
It could be. That's one example.
Mm-hmm. And then, so does it mean that then that this explosive energy release stuff can happen only in a chaotic system?
I don't think it can only happen in a chaotic system.
That's what I would have thought. Mm-hmm.
I don't think you need chaos for that.
Mm-hmm. But you do connect it with the non-integrable solution. That's why I asked.
Yeah. Well, I would love to talk more about this. Talk shop more about this. I know that I'm over time, but please email me, and I would love to talk about it.
Wonderful. Thanks.
Yeah.
Any other questions for Jay? So I have one question while we wait for others to. Oh, Ilan, do you have a question?
Yeah, just a short
Go
comment.
ahead. Go ahead.
So I have three tiny comments. First, the mathematical aspect of the fact that thermal Maxwellian distributions are creating a basis, which is correct. And therefore, in principle, if you have enough thermal distribution, you can fit almost anything. Then there's the question, if, as here, the story is, the resonant interaction between the waves and particles accelerates or creates some new distribution, like in your case, the third one. So I just thought at that moment, it's not necessary that it will be immediately creating thermal. And this is a question, probably it's not that important, just to have additional distribution at high velocity with some spread, it's enough. So this is a more general question of the mathematical approach. And we do it always because with thermal distribution, we have all the machinery how to do it. And then I have two sort of facetious comments about the comment of the mixing and unmixing. I think it was in the poem. I recall that in chemistry, there is relatively famous Jabotinsky equation that you mix. Okay, if you mix two entities and you create really mixed distribution, eventually, if the two entities have some intrinsic structure, you recreate back the previous unmixed part. And there are some experiments. I remember the name Jabotinsky, that's all. That's a comment. And
Right. So may I say something about that?
Sure.
So it's actually really interesting because in the 1960s, plasma physicists were beginning to think about this, but that was before mathematicians were able to correctly describe what was going on. So for what you just said was a reversible, you just said that was a reversible process. But in theory, if it's really chaotic and really is thoroughly mixed, the process would not be reversible. It would be irreversible.
Yeah, I agree. I just wanted to raise some questions that sometimes it can be, the entropy is not necessarily always increasing depending on the system. So that's a comment which can be discussed.
Right.
And third one is also some curious story that at the end you described it's called the cascading of the phenomena with the knots.
Oh yeah.
And this comes immediately to my mind, the famous story of 19th century when they did not know anything about the structure of atoms, and only we knew a little bit about some ions, some atoms, some few of them. And then Lord Kelvin suggested this fascinating idea that hydrogen, oxygen, whatever was known, helium, I'm not sure if helium was known already, but there were many quiet elements. They differ by topological internal structure. And these structures have intrinsic invariance, which is very difficult to break. So it's completely wrong in this context. We know what happened, but I know also that recently in the field theory and in advanced mathematical description of particle physics, there are so-called scarmions and many other new phenomena. So they bring back the story. So that's my comment.
Scarmions?
Yes, you can.
I'm gonna look that up.
It's very famous story now in, I don't know, in particle physics. So.
Okay, cool. I'm gonna look that up. Thank you.
Thanks, Ilan, for that comment. So I wanted to very briefly, if there are any other questions, otherwise I'll just make one general comment. So one thing that I think fascinating that in these early probe observations is that there are some intervals of very quiet solar wind, as you said, but most of the time, whether it's slow or whether it's faster, and except perhaps in the near neighborhood of the current sheet, it seems that there's Alfvén waves always there. And so the question I had is, perhaps one should generalize kind of all the stability studies of distribution functions, including some level of fluctuations as kind of part of the original system itself. These particles are always embedded in a bath of these fluctuations, probably originating in the lower corona somewhere. And so I wonder how that would change the description and the stability properties of some of these particles, of these particle distribution functions.
Yeah, I absolutely agree with you.
Yeah, so it was. I think it's interesting if in the end. So because the other thing is that in the old simplistic view of the difference between the sort of fast wind and slow wind was that the coronal whole wind is accelerated and heated continuously because you have this flux of waves that survives, but the sort of the slow wind, it looked like you put a bomb in the corona and then you just let it go more or less adiabatically. That was like the early view of the difference between fast and slow. And I think what we're happening is that we're going to discover that there's a whole series of intermediate steps in this.
Oh yeah. Oh yeah. I think that the ideas of slow and fast wind and characterizing what waves will come about in slow wind and fast wind. I mean, I think that those ideas should be revisited because we're seeing all new classes of different types of wind.
Right. All right. If there are any other final comments or questions? If not, thanks, Jay, for this illuminating talk, and thanks for your poem, which appreciated. And thanks, everyone. And we'll see you all again for the next seminar in our series, which will be probably later in the month of June, because in June we also have the Parker 1 conference, which is in the 3rd week of June. And so we're going to probably postpone our HERMES seminar to the 4th week of June. But really, thanks a lot, Jay, for this really interesting talk.
Well, thanks everyone for coming.
Thanks. Bye.
Bye bye.
Goodbye.